behind schedule, so we do get a quick start. So it gives me great pleasure to introduce our next speaker, David Kaiser. David and I have been talking about loopholes for 1.5 years. So now we've got loopholes, Bell's Inequality, and he's found some more patched up some on the left.
Thank you, Simon. Thank you. It's a great pleasure to be here today. Stimulating start. I'm excited for the rest of our discussions throughout today and tomorrow. It's a wonderful day to have discussion. I don't know if I'm surprised as I first mentioned today, as some of you don't know, is World Quantum Day. I think it's the 3rd annual, so this is thanks to the lobbying effort of Big Quantum. We have this now every year, building up to the quantum centenary. We'll all celebrate this soon. Of course, other good reasons to come together and celebrate Susan's Physics Nobel Prize, and also the book that we, at least I am so very proud of. I know the book had many associate editors, many who are in the room, but I think we know there was really one editor that ruled them all, so I want to really congratulate Olival in particular for helping us all come through this book in the world. So great reasons to come here today. I'll be very brief at part one. I'm sure many of you know this material very well. Professor Aspey summarized it for us so beautifully this morning. But I want to just make sure we're on the same page about Bell's inequality, and then I'll shift, as Simon said, to a series of loopholes that were identified often long before they were addressed experimentally. Many loopholes conceptually were identified by names we will know, including John Bell and John Clauser and Abba Shimoni and other colleagues. And then what has it taken to address those in a series of experiments, some of them quite recent, and I'll come to some of those recent ones as well. Okay, so again, as we of course illustrated very well, many discussions trace back to the 1935 paper by Einstein, Podolsky, and Rosen. I won't say too much about this. We know it was a direct inspiration for John Bell himself. So according to quantum theory, as the authors themselves clarified, if we prepare a pair of particles in a particular state, release them from the source S, send them in opposite directions, then prior to measuring either subsystem, quantum theory would describe this pair of particles as a superposition of two different two-particle states. And again, as Professor Aspey emphasized this morning, according to ordinary quantum theory, the state doesn't factorize. There's no way in ordinary quantum theory to describe, for example, the properties of particle B without already referring in some way to particle A and vice versa. And so again, in the original EPR paper, there's really a remarkable, brief but remarkable argument. Physicist 1, who's standing by detector 1, could choose to measure one of two things. These were still continuous variables with continuous spectra before we get to these dichotomic ones. Could be, for example, position or momentum along the x direction. Either choice would reveal something about the properties of the partner particle. But what had these physicists one of the things that got them so concerned was that if the physicists at detector 1 waited until the last possible moment before deciding which measurement to perform, then there wouldn't be time for a kind of update to travel at or below the speed of light to inform the now far away particle what properties it must have. And so this is why Einstein and his colleagues concluded that particle B, and therefore each particle, must in some sense carry with it on its own backs a complete set of definite properties. It can't wait to be updated because we could fool it and catch it in the lie. And yet quantum mechanics had no way to describe particle B as carrying a complete set of definite values, at least on its own. And so that's why they have this famous conclusion that quantum mechanics is incomplete. We know, again, as has been said already, roughly 30 years later, John Bell has this very squarely in mind. He names one of his most famous articles directly in response to this work by Einstein and his colleagues. And again, as we know, so now we went from a 4-page article to a 6-page article. These are all very brief but incisive interventions. Bell argues that the EPR conclusion rests, of course, on several assumptions. And ultimately, these assumptions could be tested. We don't have to agree or disagree late at night through the fog of cigar smoke, so that's also fun. Bell suggests maybe we could actually subject some of these assumptions or rival sets of expectations to laboratory tests. And so as we get what we still call this day Bell tests, shown here in cartoon form, I would say this is what experiments look like to a theorist, not to someone like Professor Aspey. This is a blueprint of what one might then try to make real. a source of entangled particles in the center. They head off in opposite directions toward identical detectors. And just to clarify the nomenclature, the small letters, lowercase letters, indicate the choice of measurement bases, which question will be asked of that particle when it arrives, and the larger capital letters are the outcomes. So we might choose to measure spin along the x direction, and the outcome will be, say, spin up. Okay, that's the sort of typical nomenclature here. And again, as we heard this morning, one of the innovations that Bell incorporated from Bohm's previous discussion was to focus on dichotomic observables, spin up or down, polarization of photons, yes-no questions, or anything that could be put in the form of a +1 or a -1. Then it's particularly simple to construct these correlation functions. Compare the measurement outcomes at detector A and detector B as one varies the detector settings at each location. And then in a form slightly different than Bell's original, as we heard, this is a form introduced a few years later by Kaiser, Horn, Shimoni, and Holt, so-called CHSH inequality. By constructing a particular combination of those comparisons, then Bell can really work his magic. And here's we get to these locally causal models. Any model, is why it's a very powerful no-go theorem, any model of the micro-world that can be put in this form as a series of conditional probabilities. What are the probabilities to get particular measurement outcomes, big A and big B, upon having chosen to perform certain measurements, little a and little b? If that could be written in this abstract form, where you have some supplementary parameters, so-called hidden variables, but such that the probability to get a certain outcome at one detector cannot depend on what happens at the far detector, either the decision of what to measure or the measurement outcome itself. This is what came to be called local causality, sometimes called Bell locality, and so on. Any model of the microworld that can be put in that form must obey this inequality, that the measurements can only be so correlated and not more so, that the strength of this parameter S is bounded to be between -2 and +2. And of course, as was already well known by that time, it's quite straightforward to find examples from ordinary quantum theory that suggest a very strong violation. It's worth pausing here. 2 times the square root of 2 is a lot bigger than 2. And that gets experimentalists, or some experimentalists, interested. It's not an effect that might be lost at the fraction of a percent level. In principle, there's a very distinguishable signal if one chooses the quantum state carefully. And so the very first experiment that was ever done purposefully to test this question, could correlations exceed the bounds set by Bell's inequality, was conceptualized by John Kaiser. He had stumbled upon Bell's article kind of by accident, at least as he later recalled, as a graduate student. He was dissuaded from working on the topic because it was determined at the time not to be so-called real physics, at least by his own advisor and many colleagues. A few years went by, and then Kaiser completed his PhD in radio astronomy, early cosmology work. Got a postdoctoral appointment at the Lawrence Berkeley Laboratory in California, and this was actually a time of a real downtime in the laboratory and across certainly the United States. There was kind of excess capacity, you could say, a real financial downturn in the field, and so he asked his new faculty advisor, could he spend some of his time on this kind of pet idea that had been lodged in his mind for a few years by then. Could he work on the side to conduct an experimental test of Bell's inequality? His advisor, I think it was Charles Towns, was at least modestly supportive, in fact arranged for a graduate student at the laboratory, Stuart Friedman, to help. Here are these now famous photographs. They were literally duct taping the apparatus together. Kaiser said many years later in an interview that he got good at dumpster diving. It was not a fancy, highly funded experiment. It was on the side to try to see could this be done experimentally. And they were able to publish their results in the very prestigious Physical Review Letters in 1972, finding clear violations of Bell's inequality, as predicted by quantum mechanics, compatible with ordinary quantum theory, with high statistical significance. Inequality violated by about 5 standard deviations. So I want to contrast very quickly that first experiment in a laboratory in 1972 to experiments now being done routinely around the world. This also was mentioned briefly by Professor Espay. One of my favorites, and many that I love. This one I love for its ambitions. A large group led by Professor Zhenwei Pan, supported by the Chinese Academy of Sciences. They built and launched a purpose-built satellite that to this day is beaming down pairs of polarization entangled photons. And now people can conduct Bell tests 1,200 kilometers apart, not 6 meters apart with duct tape. How far are they at least? It's kind of amazing. Okay. So one might say, okay, we've had now 50 plus years of experiments, we're done, right? Locally causal models are incompatible with the world. And yet, as was also realized by people like John Bell himself, like Kaiser and Shimoni and Michael Horn and others, that conclusion that we're done, that nature is incompatible with locally causal models, that relies on several assumptions. Bell's theorem is a theorem. It follows if the postulates hold. How do we know those postulates hold? Can you instantiate in an actual laboratory test the assumptions within which or from which would follow the conclusion of Bell's theorem? And so a lot of its early discussion was handled in these sort of informal, hand-typed mimeographed newsletters. We'll hear about later at our meeting in a collection now called Epistemological Letters. This was not fancy, high-end stuff. Already by the late 1970s, again, as many of you may know, John Kaiser and Abdul Shimoni had written a really remarkable review article that still rewards going back to today, collecting what had been known by the late 70s, not quite 15 years into the era of Bell's inequality, about the theorem itself, about the early experimental tests, and often articulating many of these loopholes. So the existence of these loopholes goes back many of them to the 1970s. The first to be identified is one, again, we've heard much about this morning. It's now often called the locality loophole. It's really asking, was there an opportunity for inadvertent or hidden communication between parties, and could that very mundane explanation account for these highly correlated outcomes of the measurements? And so if one is not very careful and considers this kind of space-time arrangement for the specific events within a Bell test, if one first decides which measurements to perform, setting little a and b, then one goes for lunch, or has a nice espresso, come back, turn on the laser, emit your particles, and then measure particle A, but wait a while, then measure if we're sloppy with our space-time arrangement, then there's all kinds of opportunities for quite mundane explanations completely consistent with local causality that could account for why the measured outcomes exceed Bell's result. And so instead, as we heard earlier, one has to be very precise in the space-time arrangement of the relevant events. So as was discussed even in letters, I think Olival had found, I learned of at least from Olival's historical work, some letters between John Kaiser and John Bell in 1969, they were already saying to really be persuasive, one should select the measurements to perform while the entangled particles are in flight. Emit the particles first, while they've left their kind of home source central location, only once they're apart from each other decide which measurements to perform, and also complete each measurement in space-like separated fashion. Then you sort of foreclose that kind of explanation that otherwise could have in principle accounted for these highly correlated outcomes. And that of course brings us to Professor Aspey, who then set this as a remarkable goal early in his career, beginning early mid-1970s. It was, as we heard, a series, a culmination of a whole set of experiments, the one that was especially focusing on what we now call the Locality Loophole, published in 1982. And again, as we heard, the idea was to set up these very fast-switching acoustico-optical switches, which actually had, if I remember correctly, could change basically the choice of measurement to perform on each side every 10 nanoseconds. If you're dealing with photons in a laboratory-sized room, you really have a very tiny time budget to make things line up for these space-time diagrams. So the detectors are now further apart than even in the Freeman-Klauser experiment, a longer baseline for photons to travel. And so the choice of what measurement to perform really was changing after the entangled photons had been emitted, and indeed, in addition, completing each measurement in a space-like separated fashion, which also had not been done in the earlier experiment. And so with these kind of precautions in place, these really quite amazing experimental improvements, then Professor Aspey and his colleagues found, again, a compelling violation of Bell's inequality, exactly as expected by quantum theory. Again, as we heard this morning, about 5.5 standard deviations. Now shielding against that first of these so-called loopholes that could have otherwise accounted for something like Freeman and Klauser's results. Professor Aspey himself had noted in this magnificent article that his technique was actually periodic in time. Acoustico-optical switches were moving on a, in principle, predictable pattern. So even in the first terrific article, Professor Aspey and colleagues said, actually, in principle, if one's really stubborn and wants to be kind of a stubborn Einsteinian or advocate of local causality, one could imagine that information about the measurements to be conducted would have been in principle available at the source before the particles were emitted, because it's a predictable, at least in principle, predictable pattern of when the switches, how the switches would change. And so that's when another one of this year's laureates, Anton Zeilinger, set about with his group many years later, in the late 1990s, to try to address the locality loophole without this sort of periodicity. So again, being very attentive to the space-time arrangement. When do you emit the particles? When do you select the measurements to perform? How do you complete each measurement? But now inducing the choice of what to measure by using a quantum random number generator or a QRNG. And these have developed a lot since then. In the late 90s, what they did was very clever. Took a light-emitting source, an LED, and shown that light, not the entangled photons, a separate photon, part of the instrumentation, shown the output of the LED onto a beam splitter, and then whether that photon gets through or not becomes your quasi-random number, 0 or 1. Now I have a remarkably rapid duty cycle. They can output quasi-random bits, 0s and 1s, every 2 nanoseconds, whereas they also are now working in this experiment hundreds of meters apart for the entangled particle flight time, so really ensuring the space-time arrangement. And again, with all these precautions in place, find a very, very clear and compelling violation of Bell's inequality. Okay. So this first loophole was identified in 1969, before the first experiment had even been conducted, involved, as I hope you can appreciate even from this brief lightning review, several very, very complicated technological implementations. Identifying the challenge is different than really addressing it in the laboratory, but with this growing series of experiments by in the 80s and 90s, one could argue quite on strong evidence that this first loophole had really been closed, and one still finds clear violations of Bell's inequality. Okay, that was the first loophole. There were at least 2 others that were identified around the same time. So conceptually distinct, a kind of orthogonal thing to worry about in these Bell tests, was not about hidden communication, but rather about the collection of particles you successfully measure. So this loophole to this day is known in the literature as the fair sampling, or sometimes the detector efficiency loophole. This had nothing to do with hidden communication per se. This actually now goes to, again, how real experiments are conducted. No detector, even to this day, can reliably measure every single particle that impinges upon it. They've gotten extremely good, but not literally 100%. In the olden days, they were actually much, much less efficient. So the argument, well, again, articulated to my knowledge first by Philip Pearl, I think somewhat into maybe Flavio, so there might even be an earlier example, at least as early as 1970, theorists were realizing that this could be a distinct way by which a locally causal model could evade the Bell's theorem and reproduce all the expected measurement statistics of ordinary quantum mechanics. The idea would be that if you only catch a limited sample of all the pairs of particles that are emitted, what if there's something funny about that biased subsample that's not representative of every single pair of particles that have been produced and emitted? And not only is that a possibility statistically, again, in many of these early papers, people built sort of funny-looking but internally self-consistent, locally causal models that could exploit this loophole to reproduce the measurement statistics of ordinary quantum mechanics. To evade this kind of argument, again, people were calculating by the mid to late 80s and 90s, this was really a technology game. One needed to improve the efficiency above a threshold, so the number of particles one missed would be insufficient to amount the statistical argument. Okay? And that was again articulated between the 70s into the early 90s. And yet it wasn't even attempted experimentally, not successfully at least, until the early 2000s. So again, a huge gap in time between identifying this challenge conceptually and mounting experiments that could successfully measure Bell's inequality while closing down this kind of loophole. So the first systems were done with basically slow-moving atomic systems, ions and magnetic traps, superconducting qubits. It was first done for photons only as recently as 2013 with very fancy, super cooled single photon detectors. That's how challenging this was technologically. The earlier experiments were done with, let's say, with these sort of penning traps, where you could trap ions and sort of have confidence that you're getting a majority of the sample. All this was so hard that these experiments that successfully closed loophole 2 had not even tried to close loophole 1. So with the traps, they're so close together, they're not even trying to shield against the possibility of hidden communication traveling at or below the speed of light. So by as late as 2013, we had a population of beautiful experiments by a growing number of groups around the world that had closed either loophole 1 but left loophole 2 open, or the opposite. That changed, again, as we heard this morning, quite dramatically in the closing months of 2015. Suddenly we've gone from 1935 to 1964 to 2015, the first of several experiments around the world that successfully closed both of those loopholes in the same experiment and still found statistically significant violations of Bell's inequality. So one could no longer appeal if one were a devoted, locally causal advocate. After these experiments, like the one led by Robert Hansen at TU Delft, and I'll show you some of Well, I'll just skip that. So anyway, this was, again, headline news in the New York Times, the first experiment of several, it turns out, to successfully close both of those loopholes at once, followed close on its heels by very similar conceptually pair of experiments. They're using different entangled systems, now back to polarization entangled photons.
Alors, professeur, comment vas-tu? C'était juste pour te dire, tu sais combien tu peux pour ton oral là? C'est fini là. T'en as 20, ça va hein? Eh oui. Non, parce qu'aujourd'hui c'est le dernier jour. Enfin, midi c'était la limite, tu vois. Moi j'ai eu 28. Et Gamibert 21. Quoi. Malheureusement Gamibert il t'a battu d'une place. Quoi, tu vois. Ah, il va devoir travailler. Ah, je sais, elle m'a appelé, mais moi je suis en CP là. Ah ben merci, j'ai même pas allumé mon titre. Je vais l'appeler sur la... Oh, on sait. Ah oui, c'est
Okay, so very soon after the TU Delft experiment, these pair of experiments done also independently from each other, one again by Anton Zeiliger's group in Vienna, another led by Christa Schalm at the National Institutes of Science and Technology in Boulder, Colorado. They each also succeeded with different experimental systems to test Bell's inequality closing these two loopholes. I'll just say briefly, I had a chance to visit with the lead author of Anton Group's experiment, Marissa Justina, while the experiment was underway. Here, it was conducted in the basement of the Hofburg Palace in Vienna city center. They needed 60 meters of quiet, undisturbed space along which to string this very carefully shielded fiber optics. You have to make sure you don't miss a single photon or very few photons. And so I like to say that many grad students imagine that their dissertation work it feels like being locked in the dungeon of a castle. Marissa was actually locked in the dungeon of a castle for 5 years and managed to do this really quite beautiful experiment. Okay, that's loopholes 1 and 2. Again, as identified very early in the discussions of Bell's inequality, was a third conceptually distinct loophole. It's known by many names. Nowadays, it's often referred to as freedom of choice. That name might not be everyone's favorite. You might know it better by either measurement dependence or sometimes called settings independence loophole. Again, the more recent literature now fills many journals. It goes back again to a debate, much of it carried out in epistemological letters, not sort of formal journals, in the mid-1970s between Shimoni, Glauser, Horn, Bell, and then other colleagues. Finally weighed in on this as well, actually, the paper that Professor Spey reminded us of. What's the idea? The idea here is to ask, are there any statistical correlations between the choices of measurements to perform, these detector settings, and the properties of the particles, as reflected, for example, in the shared hidden variable? That's a distinct kind of loophole, then, did one photon talk directly to the other? So if we go back to these conditional probabilities, what we're really saying is that if the conditional probability here to measure particular outcomes, capital A and B, is conditioned on a choice of measurements to perform, then just as a basic rule of statistics, one has to propagate that through. It's the moral equivalent of the chain rule in ordinary calculus. Then in principle at least, then each of the quantities within your integrand could have, one must consider the possibility of a conditional dependence there as well, okay? And so this is called, to the statisticians, the law of total probability. Bell had tacitly left that out. He, in fact, had not said anything about it in the early work. This was pointed out to him in the mid-70s by people like Clauser, Shimoni, and Horn. And by Bayes' theorem, if you ignore the possibility that the choice of lambda could have been conditioned on the choice of measurements to perform, that's equivalent to have assumed that the choice of measurements to perform had no possible correlation with the properties of particles. And Bell concedes this point, again, in this early debate, where he says, it had been assumed in his original derivation that the settings of the instruments are in some sense free variables, that's where the name comes from, at the whim of the experimenters, or in any case not determined in the overlap of the past light codes. It turns out this more recent theoretical work since the early 2010s, if one allows for the possibility of some statistical correlations between the properties of those particles produced and the choice of measurements to perform, then in fact Bell's inequality is most vulnerable to this form of locally causal, let's say, cheating or workaround. It takes more than 20 times less coordination, statistically, for a locally causal model to mimic all the measurement statistics of the quantum singlet state than it would if you exchange even a single bit. It takes less than 1/22nd of a bit of so-called mutual information to mount a simulation quantum theory with a locally causal model if one exploits this third conceptually distinct loophole. So what are we to do? If we're not going to simply assume by fiat that there's no possible coordination between these quantities, then how might you address it? Just very briefly, the last main part. There have been several efforts in the literature. I'll go ahead to one of the first, which got some fun attention, published in 2018, conducted in November 2016. A consortium of laboratories around the world, some of you know this, right? 12 laboratories, 11 countries, 5 continents. That's world quantum day for you, right? Plus 100,000 internet-recruited volunteers. What could go wrong with asking lots of strangers on the internet to help you with your research? So these so-called Belster volunteers. The volunteers played a prefabricated online video game on their smart devices, because what else would they do? And the game was to be as random as one could. And this algorithm had a machine learning algorithm that would learn your own patterns, so you got points, which is what video games are about, if you became more random than the machine had predicted you would be. So you have 100,000 people trying to basically produce random patterns of zeros and ones, beating a robot that tries to model their own behaviors. Those then get piped by a very sophisticated internet assembly to become the random inputs for those 12 laboratories in real time over the course of one 24-hour day. So they crowdsourced the randomness, and every single laboratory found compelling violations of Bell's inequality. What my friends and I did was not to rely on the kindness of 100,000 strangers, but instead of crowdsourcing, we wanted to outsource. We wanted to turn the universe itself into a pair of uncorrelated random number generators. So the idea was to appeal to a seemingly random, or at least faraway processes in the sky that had happened long ago and far away, separated by enormous cosmic distances in space and time from the rest of our experimental apparatus. So we used real-time observations of high redshift astronomical objects. Those became more random zeros and ones in our own experiment. Here's a quick map of the history of the universe as I like to think of it. This is not drawn to scale. In the beginning was the Big Bang. We were just thinking before then. We can discuss that too. And then some while later, some hot blob of matter began to emit light. That's one quasar, one side of the sky. A little while later, some other blob of matter condensed began to shine as a separate high redshift quasar on the opposite side of the sky. Light from those emission events had been traveling toward the Earth for the rest of cosmic history, in this case for 12 billion years, in one of our large quasars. While that light is racing toward the Earth, before that particular astronomical emission event had been received at the Earth, so while the astronomical light is traveling toward us, we then turn on our laser, create entangled pairs of photons on the Earth. After the entangled photons are emitted, we then measure very quickly the astronomical signals. Those become our real-time random inputs for measurements to perform, and then we also complete the measurements in space-like separated fashion. Because this protocol, a locally causal explanation would still be possible if something within the past light cone of either emission event had either influenced what would be emitted or gotten a preview and shared that. So our protocol bounds by the more recent of the two emission events, the most recent time by which a locally causal model could have exploited this freedom of choice loophole. And the last thing on these plots to keep in mind is sometime between the Big Bang and when you turn on your laser, you have to get the funding, and that actually was really non-trivial. That was the hardest part of this experiment. And that brought us to the top of the island observatory of La Palma in the Canary Islands, absolutely breathtaking photo taken by one of the grad students working in our group above the cloud lines. So very briefly, here was our experiment on the mountaintop conducted in January 2018. 3 main stations, the transmitter and then 2 detector stations. Here's where we shipped, actually from Anton's laboratory in Vienna, in a shipping crate, our optics lab. So our pump laser, nonlinear crystal, and so on, to create and beam out pairs of polarization entangled photons. And they're detected about half a kilometer apart in opposite directions. So it looks like to do the alignment optics. So we're able to close the locality loophole, the space-time ordering of events of both when does a random choice get received from the sky, when did the causal wave front from that emission event reach the other parts of the experiment? We have to be careful about that. When were the particles, earthbound particles emitted, measurements completed, all that. So we close the locality loophole, loophole 1. This is free space transmission of photons. We're missing a lot. So we were not able to close loophole 2. We were subject to what's called the fair sampling loophole. That's what we could do. But we tried actually to address that third loophole in a cosmic way. So we got to use these absolutely gorgeous instruments, the Galileo National Telescope and the William Herschel Telescope. Both of these are 4-meter optical telescopes, among the largest optical telescopes on the planet. We got to use 2 of them at the same time because Professor Zeilinger is very persuasive. So he talked his way into this amazing deal. Astronomers give us observing time for a few nights in January. Okay. So what's our randomness from the sky? If you measure the light from a high redshift quasar in very short intervals, then you have random-looking fluctuations in the frequency you measure, sometimes more blue than average, sometimes more red. That's what becomes our astronomical random number generator with a 20 nanosecond latency. We're getting random-looking zeros and ones every 20 nanoseconds from inputs on opposite sides of the sky. That's happening while the entangled pair is already in flight across the island. We did that with 20,000 pairs of entangled photons, found very clear violations of Bell's inequality, while ruling out, or constraining this third loophole, eliminating that explanation from 96% of the space-time volume of the past light cone of our experiment since the dawn of time. So it's 4%. So, say in parallel with us, John Pan's group was able to close loopholes 1 and 2, use smaller telescopes closer together, and push back this freedom of choice loophole by about 11 years, using very bright nearby stars within our own galaxy. Same idea, an absolute brilliant experiment. So to close, I'm sorry I'm running long, we had this remarkable timeline, 90 years of people thinking very hard about this topic, and yet enormous gaps, 30 years, 10 years, and so on. The conceptual loopholes identified early, and yet decades later before many of them were addressed. And only since 2015 have we as a community had compelling experiments closing at least pairs of loopholes in the same experiment. So whereas the ideas are very old and many of the experiments are path-breaking for themselves, we're in a newer phase now, a phase that now helps generate continued excitement with more than $1 billion of annual expenditures in related areas. So when we come to things like quantum encrypted video conferences across continents, protected in principle by entanglement with these ARC protocols, we don't have to worry about these loopholes because even if nature doesn't exploit them, people could. So a lot of the funding and impetus to pursue these loophole-free tests is because bad actors among ourselves, even if nature doesn't, could actually exploit each of these loopholes to try to fake the safety of a quantum encryption channel. So we'll stop there. We've come quite a long way from the days of epistemological letters, and again, I want to thank Oliver and our colleagues for getting this book into the world. Thank you.
We're at such huge time constraints that there's no time for questions. I'm sorry.
Of course, I'm happy to chat at conference.
So, and if everybody goes over 5 minutes, we're going to be an hour later for dinner tonight. So please, can we keep to the time? So our next speaker, Daniela.